In this video, we're going to explore the Pythagorean identity. Now, from your previous work, you can recognise the unit circle, and we have a point P placed in the first quadrant, and it has an angle made theta. Now, if we were trying to work out the coordinate of P, we know that we're going to be travelling along the unit circle along the x-axis and then vertically up parallel to the y-axis. Now, if we were using Pythagoras' theorem, we would say x squared plus y squared equals the hypotenuse squared, and the hypotenuse obviously is 1, so 1 squared is 1. But in using trigonometry, we would represent the x value as cos theta, and we would represent the y value as sine theta. So taking this idea, we have the Pythagorean identity, that's cos squared theta plus sine squared theta equals 1. We know that this holds true for all values of theta, hence it is called an identity. But let's consider some alternatives to the Pythagorean identity. Let's take our identity and divide every term by cos squared theta. So we've got sine squared theta over cos squared theta plus cos squared theta over cos squared theta equals 1 over cos squared theta. Now we know sine squared theta over cos squared theta is tan squared theta, and cos squared theta and cos squared theta is 1, and 1 over cos squared theta will be sec squared theta. And what we've come up with is an alternative to the Pythagorean identity. Let's do that again, but let's divide by sine squared theta. So sine squared theta plus cos squared theta, or cos squared plus sine squared, equals 1. We're going to divide through by sine squared theta. And then we can simplify this because sine squared over sine squared is 1. Cos squared over sine squared is 1 over tan squared theta, and 1 over sine squared is the cosec squared theta. Now we can go a little bit further because we know that 1 on tan squared theta is going to be cot squared theta, the cotangent. And what we've come up with is an alternative way to represent the Pythagorean identity. So in fact, we've got 3 forms to consider this identity. They do come in handy when we're trying to solve or manipulate certain expressions. So let's take a look at some of those now. So in our first question, it says express 4 sine squared theta plus cos theta in terms of cos theta. Now, so we want to get rid of the sine squared theta. Well, straight away, we can manipulate our original Pythagorean identity, cos squared theta plus sine squared theta equals 1. We can rearrange this to say cos squared theta is represented by 1 minus sine squared theta. So we can input, let's turn that around the other way. It actually would help us much better. Sine squared theta equals 1 minus cos squared theta. So we can input 1 minus cos squared theta where we would have the sine squared theta. So let's do that. So 4 times 1 minus cos squared theta plus cos theta. So now we've just got cos thetas involved. So this equals 4, take 4 cos squared theta plus cos theta. It's looking very, very much like the quadratic, so I'm just going to put it in that way so we can see the reduction in that term. So what I'd like you to do now is pause the video and have a look at expressing sec squared theta plus 2 in terms of sine theta. And my clue here is to go back to one of the alternative forms of the Pythagorean identity where sec squared theta was involved. Okay, let's take a look. So we can replace the sec squared theta with 1 plus tan squared theta plus 2. We want it in terms of sine. Let's collect the 1 and 2. Tan squared theta is the same as sine squared theta over cos squared theta. And I know I can replace the cos squared theta using the original Pythagorean identity by saying 1 minus sine squared theta. I've run out of room, so I'm just going to bring it up to the right. So we've got one solution here. I could place them all over a common denominator if I wanted to by multiplying through by sine squared theta over sine squared theta on the 3. And then that would give me the following simplification if you wanted to create a single fraction. So now let's consider if we're trying to solve for all values of theta in radians. We've got 2 sine squared theta take 3 cos theta equals 0. Well, straight away I'm now going to want them to put them either in terms of sine or cos, so I'm going to go for cos this time. So I'm going to use the original Pythagorean identity. So I'm going to replace sine squared theta with 1 minus cos squared theta. Take 3 cos theta equals 0. So I've got 2 take 2 cos squared theta take 3 cos theta equals 0. It's looking very much like a quadratic, so I'm going to pretend I've moved all of this to the right side or multiplied through by -1. 2 cos squared theta plus 3 cos theta take 2 equals 0. So I can factorise this into 2 cos theta and cos theta and a take 1 and a plus 2. I'm just going to check that's going to multiply out to give me what I want. So let's take the first possible solution, cos theta equaling 1/2. Therefore, theta reference of 1/2 would be pi on 3. It's going to be plus or minus pi on 3 plus 2 pi n when n is an integer. Or our other solution, cos theta equals -2. No solution exists here. So now I'd like you to pause the video again and have a look at number 4. Solving sec square theta. Take the square root of 3 tan theta minus 1 equals 0 for all values of theta in radians. So again, we've got sec squared theta involved here and a tan. So I think we could look back at one of our alternative identities for the Pythagorean identity, since sec squared theta is involved, and substitute the sec squared theta for 1 plus tan squared theta. So pause the video and have a go. Okay, so I'm going to replace 1 plus tan squared theta here instead of sec squared theta. And now I've got it all in terms of tan. Once again, I can see that I've got the format of a quadratic almost. But the plus 1 and take 1 are going to cancel. So I'm going to take out a common factor of tan theta, which will leave tan theta minus root 3. So 2 sets of possible solutions to consider. So if tan theta equals 0, well, this is going to occur pi n when n is an integer. And our other possible solution, tan theta equaling root 3, so that has a reference angle of pi on 3, and that will happen every pi degrees, radians. And I can state all values of those solutions. So our ideal is we want to prove certain statements or identities. And we can use a whole lot of the things that we do know, the facts, to help us prove them. In a proof, essentially we want to choose one of the sides, the left-hand side or the right-hand side, and start with one of them and show that it equates to the other. So let's begin with our first example here. Prove 1 plus tan squared x equals sec squared x. So this is one of our alternate Pythagorean identities. I'm going to start with the left-hand side. I'm going to change the tan squared x to sine squared x over cos squared x. I'm going to change my 1 whole into cos squared x over cos squared x, so they've got a common denominator, so I can add these two fractions together into 1 whole fraction. So I've got cos squared x plus sine squared x. This looks very, very familiar. I know that this equals the original Pythagorean identity, which is going to make it 1 over cos squared x. Fortunately, I've run out of room. So this equals 1 over cos is going to be sec, so this is going to equal sec squared theta, and in our case equals the right-hand side. So now it's your turn. I want you to pause the video and have a go at number 6, which is proving the other alternative to the Pythagorean identity. Oops. So you can check your solution of your proof for question 6. In question 7, we've got tan x takes sine x times cos x equals sine squared x tan x. So again, I'm going to take the left-hand side. Having a look at what I want it to equal, I'm going from 2 terms down to 1 term, and I've got a sine squared. So the first thing I'm going to do is change my tan x into sine x over cos x on the left-hand side. I'm going to then make sure they've got a common denominator for these 2 terms. So I'm going to multiply the second term by cos x, and then I can place them all over cos x. So it's going to make that one cos squared x. The reason I'm going to do that means I can take out a common factor of sine x, and that's over cos x. And sine x over cos x is tan x times 1 minus cos squared x. And this part here in yellow reminds me of the Pythagorean identity. This equals sine squared x, and I've equaled the right-hand side. So now it's your turn to pause the video for the last time and have a go at the following proof.